Okay, good morning and welcome to the second day of the workshop. And we're very happy to have a local expert on lattice gauge theory, Professor Colin Morningstar, tell us about Glueballs, etc.
Thank you very much for the introduction and the invitation to come and talk. I'll be presenting. So this is for the Zoom, right? So I shouldn't go too far from it, or it'll pick me up. Can you still hear me on Zoom?
It's better to stand
If I stand here, okay. So I'll be showing you some old results and some new results. So basically some results we've had on Glueballs and the static quark potential, and some recent stuff on hadron resonances. In particular, I'm very excited about our delta and 14/5 results. Here's an outline of my talk, which is basically what I just said. All of my results depend on being able to extract a spectrum of energies in finite volume. Because we do our lattice simulations in finite volume out of necessity, momenta are quantized, so the energies are discrete. So we just have a bunch of stationary states, and we have to measure those energies or calculate those energies or estimate those energies, pick your favorite verb. And we need to get more than just the lowest line. We need to get as many excited states as we can to carry out the next step of the calculation to get information about the resonances, which I'll discuss quickly. And so basically the way to do this is to build up a correlator matrix. So we have a bunch of operators that we hope create the states of interest, but they also create higher lying states as well. Can't avoid that. And there's a spectral representation for the matrices of this these temporal corridors. Now we're working in imaginary time, so that's why you have these exponential fall-offs instead of an oscillatory factor. Now it's impractical to do fits to this form, and so typically to pull out these, some number of lowest lying energies, we do a very particular rotation of the matrix that diagonalizes it as much as possible. And then typically we do single exponential or two exponential fits, sometimes even more if we put in some Bayesian priors to extract these energies. So let me talk about Glueballs first. There's a very long history of the pure gauge Glueball spectrum, so no quarks, just gluons. This dates back really to the beginning of lattice QCD in the 1970s, when the first sort of calculations being done. These are very difficult to pull off because they're very noisy, and it turns out these Glueballs are quite heavy, so the correlators fall off very quickly, and the signal to noise is especially brutal. A lot of progress was made in the 80s and 90s, building extended and smeared operators by these gentlemen. And the last ingredient really for pulling off the spectrum I'll show you was the use of anisotropic lattices that my collaborator, my peer, and I put in the late 90s to get better resolution of the correlator so you can extract the unit. So this is sort of what the typical operators look like. We express our gluons in terms of these things called linked variables, which are just path ordered exponentials of the gauge field. And Mike Tepper, through his hard work in the 80s, and Chris Michael learned how to make a large subset of these things very efficiently, so that you could do that correlator rotation and get a very good signal. And so here's a plot of our spectrum. Our first one was in, I think, 1999, but then We repeated it in 2006 and didn't improve much on it. It's really hard to improve on this. Because there's a law of diminishing returns. You can hit it with more and more statistics. But then you start to see the higher lying exponentials, and then you have to add an exponential to your fit, and there goes the error. So it's really hard to beat down the error on these things. So the mass ratios are well determined here, but the absolute scale, that's ambiguous because we don't live in a world where there are no quarks. So it's hard to, figure out what the scale should be. Typically, people use the string tension from the formula potential if they do that. We find that this lightest scale is around 1600. This mass gap here is the only one that I know that has a bounty on its head. So if you can explain it theoretically, this Clay Mathematics Institute will give you $1 million. At the turn of the millennium was something, right? Now it's not so much.
That's what we're here for, all of us.
Well, yeah, you should ask them to increase the price.
Driven by greed.
Yes. You can understand that spectrum very qualitatively. There's a paper by these gentlemen in '86 just based on operators of increasing dimension. And if you look at these operators and look at their quantum numbers, it actually doesn't do a bad job of explaining in particular why there's no low line 0 plus or minus or low line plus global. I remember I was working with Julius Kuti at the UC San Diego at the time when I finally finished calculus. And he was a big model person. He said, I bet you I can explain this with the bag model, but he recognized that the parameters used back in the original bag model papers would not work. So he just made some quick changes to these two, and it actually doesn't do too bad a job qualitative. So the orange would be his thing. There was another popular model at the time, it was the path model, which, as you can see, does not explore the spec. So why are Glueballs, including quarks, so hard? It's because these things are quite heavy, supposedly at around 1600 MeV, and with the way we calculate energies with those correlator matrices, and you have to calculate all the energies up to that level. So you have to get all the levels below it to see that level. You have to saturate all the lowest lying stationary states. And there are many 2 meson, 3 meson, and even 4 meson levels expected. So it's very hard. And these 2 meson correlators require what are called time slice and time slice propagators. I won't say too much about it, but you need technology that we only now have. We didn't have it 10 years ago or more. You expect Glueballs to be resonances, so you have to pull the whole Lucier technology to it, which I'll briefly describe. And you, again, need high statistics because of that signal to normal. And that's really hard to get. Well, and in the scalar sector, there's a large depth subtraction. But we did try it, and here's our result. On the left here is a spectrum on a fairly small lattice and a heavy pion mass in the scalar sector. We threw in as many quark, anti-quark operators and 2 meson operators as we could. And so the spectrum we could get out using just those operators, no Glueball operators, is shown here. So the black lines would be the non-interacting level. So this is a kaon, anti-kaon at rest. This would be a 2 pion state, each one having 1 unit of momentum back to back. And so you see that can pull off the spectrum here. So we've got a large number of operators in there, but if we were to dial down the pion mass, there'd be many more. And then you'd have to have 4 particle states in there. So you can see how it becomes very little. And then we did the same calculation with the addition of a Glueball operator, just to see, do we see an additional level now? that wasn't hidden to us. All these operators could not connect to that state. And we fully expected, yes, we would see one, but we didn't. In fact, the glue balls in these two hash levels up here. So we did not find a glue ball state. So here are the overlap factors. So for example, this is for the operator, the two pions at rest. And these are the overlaps, these squared factors for each of the eigenstates. So clearly eigenstate 1 really likes that. That operator really likes that state. So we would call operator or eigenstate 1 predominantly a pi state. Yes?
Stack the Glueballs X with the Meson state, so what would you like to see?
Well, we wanted to see what would happen. So we would hope that there'd be an additional level, and then in levels near that, there would be admixtures of the glue ball operator. So it would put in a new level. I mean, it would be nice if that level alone really liked the glue ball and nothing else. Because then we could say, that's a glue ball. But realistically, we thought there'd be another level, then, 2 or 3 levels nearby, there'd be admixtures, including the glue ball. But we didn't see that.
In models, presumably you see some mixture, right? If you take a bad model.
Yeah, I don't know what the vague model says, of course. Ask Julie.
But it is not one level because of your splitting, right? It's still kind of blend of levels where your experiences evolve, right?
Correct, yeah. And you expect it to be unstable, so.
Yeah.
The levels you're gonna see in finite volume don't give you the glue ball mass or anything. You have to put it through this Lucia technology to figure out where the pole is in the scattering and so. But you need to see these extra levels or at this level. So this glue ball operator likes this 0, which I think is also this, I guess you could call it a sigma operator, a scalar QQ bar state. So level 0 is an admixture of those two operators and a little bit of strange. Where else? And it likes a little bit of 7 and 12, for example. So it seems to just connect to the levels that we saw before. And produced another level high up, but because it has to, but it's probably better. So that was disappointing.
Isn't that what we expect in science? I mean, all these things can mix, so that should just be sort of a remixture of everything.
Either that will happen, in which case, I mean, the hope was there would be one level that was predominantly the blue one. That's what we were trying to see, but we didn't see that. I guess, yeah. And in fact, we would have thought that the levels would shift around. Because in the first calculation, you're actually missing a level. Your operators aren't getting it, you would think. Or not, but. So if there is a glue ball, it's mixed. And you really have to put the Lucia, which time do I have?
About 12 minutes.
Yeah, can we discuss it offline?
No problem.
Thanks. Another thing we did years ago was looked at the static quark, anti-quark energy. At the time, we were really interested in what are called the hybrid meson. And there was some belief that conventional mesons were bound in this lowest lying potential in a sort of Born-Oppenheimer picture. And the Born-Oppenheimer picture then also said, well, there's excited levels. This pi sub u is the first excited level. You could have bound states based on this excited gluon level. We thought that would be the hybrid. And that turned out to be the case for hadron quarks anyway. But we did a large number of, I spent years doing that. So there's a very rich spectrum of these quantities here. And if you really study it at large R, large quark anti-quark separations, compared to a string model, and we try to do that. And I think there are, people are running, we've passed the baton on, there are other people looking at this now. And, I know of at least two groups that are looking at the large R, and then there's other groups looking at the small Rs. But I don't think there's anything definitive yet. You see sort of results at lattice conferences, but I don't think any really published yet. So I guess, all of our results can be found online at this website there. I just checked to see if it's still up. It's still up. So we did lots of SU3 and 4 dimensions, and SU2 and 3 dimensions, I guess. And then we took that lowest lying and the first excited and solved the Schrodinger equation to see kind of spectrum we would get out. So we got a spectrum, and then we ran some what are called non-relativistic QCD simulations, which include retardation effects and don't take the Born-Oppenheimer picture into account, just to compare energies to see if the Born-Oppenheimer had any hope of giving us a picture, and in fact we did. And in fact, we looked at about 4 level splittings, and for 4 of these hybrids. So these lines here are from the Born-Oppenheimer and these are simulations. So these splittings, which are quite small, agreed to 10% or less. So we took that, a good sign. We've even broken the string. If you're gonna have a string, you might as well break it. For a long time, people said, "Oh, you gotta hold it till it breaks," so we did. And here's our latest result. I guess this isn't exactly our latest. This is our latest, but it was more focused on quark mass dependence. But you can see this increasing potential until it becomes energetically favorable to create a 2 meson state. So now to my hadron resonances. Now I assume that these slides are published, right? Like people who will have access to it. So there's more detail than I will talk about. So if you're interested, just look at this one. So if I'm skipping slides, because I put in too much detail, so you can consult the slide with me. So how do we do it? We have to build up our operators out of what are called covariantly displaced laugh smeared quark fields. So there's a lot of technology that goes in to being able to compute these energies. And if you don't put all of these ingredients in, it's really hard. You're not going to get a signal. Just over years, we've learned what works and what doesn't. And a lot of it boils down to, here's sort of the kind of things we put in. A lot of it boils into getting rid of excited state contamination. So what you're seeing here are what we call effective masses. It's basically the logarithm derivative of these correlators. At large time, it goes to the exact energy. So these are all for a particular nucleons. And if you just build it out of a very local, unsmeared fields, you get this sort of effective mass. So it's going to the right energy, but you can see it starts off very high and takes forever. So all this in here is coupling to higher lying states, excited state contamination. So building your operators is about trying to reduce that effective mass. And a critical ingredient is smearing. And you have to smear both the gluons and the quark field. And so this is basically what happens if you link smear only and if you do both. Or this is quark smearing only. So this is a single site operator. This is one where you displace the quark and the 3 quarks, one of them, and this is triply displaced. And you see as you displace it, you get a lot more noise. So the link smearing gets rid of the noise a lot, and the quark smearing really helps. So you can see with the right amount of quark and link smearing, you can get a signal. Otherwise, it's just garbage. And for 2 particle operators, so to carry out Lucher's mechanism to go from finite volume energies to scattering phase shift information, you need multiple hadron levels. So you need to be able to compute the correlators for multi-hadron operators. And you basically have two kinds you could build. You could build operators of this nature, each one having a well-defined momentum, or you could build them in this way. Now, this is much easier for us to calculate with. We can use the point-to-all trick, which we've used for many, many years. But the problem is these operators don't work very well they have a lot of excited contamination. These are much better. So you can see the black is from this kind of operator, and the blue is from this kind of operator. So you don't even get to the expected energy of these. So you really have to use these. But once you have to use these, you have to use these time slice to time slice propagators. You can't use the point-to-all trick. And that took us a while to figure out how to do accurately, but we know how to do it now. So it's really opened up this area for us to be able to do resonances. Oops. I don't want to explain my details. So what it all boils down to is solving something like this. We call this sometimes it's called the Lucia quantization condition. So in a series of papers in the late 80s. So he did this way before it was useful to us. Paper sat there with no citation for decades. And then once we were able to do some of these tricks, he became a hero again. And then other people generalized. But it basically boils down to, there's a relationship between the finite volume energies you see and the S matrix. And it's through this quantization condition. So here's our S matrix. And there's this matrix in here that's complicated to compute, but it's well defined. And it's just a lot of cross coordinating and some weird zeta function. I don't want to go into it, but the point here is you need to parameterize this S matrix and do a bunch of fit to all the different allowed energies here to pull off. So you're using these E's that you've evaluated to figure out what this S should look like in some parameterized form. You pick a bad parameterization, you get a bad fit. And that's all I really want to emphasize. And we do it actually in terms of the K matrix. So I almost feel like a little bit of an experiment. And always dealing with the K. Because K is better than S. So this is actually the form we use in terms of K matrix with some threshold factors removed in the so-called box matrix. It's very complicated, but I spent 2 years of my life writing code to do this in memory. And I put it on GitHub, so it's available to anybody. Free of charge. Thank you. This quantization condition involves the determinant of an infinite matrix to make it practical. We transform to a block diagonal basis, and then typically we then have to truncate an orbital angular momentum. And that truncation goes very well. So here's the quick warm-up we did on the row. So this is what you have to sort of do. You have to calculate a spectrum of these predominantly two mesons. So this is for these are pi states mainly, iso triplet. So we're trying to get at the row resonance. And you need energy sort of in the energy region around where you think the row resonance will be. And then you parameterize your K matrix, but typically we use an effective range expansion. So it's easy for the inverse of the K matrix, and then you fit. And so this is the sort of thing we get out. So here's a scattering phase shift, and you see this beautiful row resonance. And we actually computed the scattering cross section. So you can actually, in lattice finite volume calculations, do scatter. Thanks to argon plot. First argon plot. Yeah, this is just putting in the L=3 and L=5 waves, and you see they had very little effect. Yeah, so I have 5 minutes, okay, and we did the K star, that was another low lying fruit. So here's the K star 892. So I really wanted to show the 2 latest results we've done on the delta resonance and our 2-pole study of the lambda 14 fall. So here's the spectrum of energy levels we evaluate. So these are our calculations, and the gray boxes represent the non-interacting energies. So it's really these small differences that are driving the Lucier quantization condition. So you can see very, very big differences here, basically coming from this is a sign of the delta. The delta resonance is in there and is really causing large shifts. You get up higher above the delta, and you can see very small shifts. So you can see the scattering there. So that was the isoquartet. This is the iso double, very small splittings from non-interacting. Why do we call it strong? Yeah, so here's then would be our fit to the cotan of the phase shift in this crossing here indicates our resonance. So we fit the mass, and this is a factor that G squared it is in the width plus phase space factors. We've tried to remove phase space factors because we're not quite working at the physical pi mass. So there are calculations now at the physical pi mass. And so we get some scattering ones. Yeah, here's one that we did not do. So at the physical point, so the pion is 140 MeV, and they studied the diaphragm. So we can do it now. The problem is the error is just still big. We'll still need to beat it down. And in fact, it's still better to do it at a series of M values that are larger and extrapolate than to do it at the physical point. The error in the extrapolation is still much smaller than the value you get at the physical point. So typically we do both. And discard the so there's the phase shift. 1 minute. And then our latest result, we wanted to study the lambda in the region of 1405 because there was a big debate over theorists and experimentalists. Is there just 1 pole there or 2 poles? So we said, well, we should be able to answer that, right? So here are the energies that we computed. See, there's some significant shifts, but a lot lying right on the non-interacting levels. And this was the first to do multi-channel. So we had the pi and K bar. And we did find that there were 2 poles. So that's kind of, so here are the poles. Here's the this is threshold factors, and then the scattering amplitude squared. So you can see the different channels kicking in. These are the 2 poles that we found. So this isn't quite physical yet. It's a 200 MeV part. And so here's more details if you're interested. Look at the slides. So here's the phase shifts for the 2 different channels, and then the inelasticity. And then we made this nice plot because they required a PRL signal. This is an editor's suggestion. We need a nice graphic. This is not a nice graphic. Too much information. So we made a nice graphic. That's kind of. Boy, it was hard. This was the hardest part of the project. All right, so just to summarize, I showed you some old Glueball results, but they're still because of the law of diminishing returns, they haven't really been improved on for 20 years for this time. And then I showed you some more static or potential results, and those haven't been improved on much either, again, for the same reason. Some string breaking, but I hope I've showed you that our ability to do multi-hadron correlators now has really opened up lattice QCD to be able to look at resonances now using this Lucier formalism. And it's been extended to 3 particles. I didn't show any 3 particle results, but we have a paper coming out, just been accepted, PRL and PRD. You know, the simultaneous submission that I really like it. For 3 particles at the physical point, but they're 3 mesons. We haven't done 3 baryons yet. One thing we want to do next is get at the Roper resonance. There was this Roper celebration this fall that I've been invited to, so it would be nice to. I don't think it's gonna happen like that. But it'd be nice to.
It's like a breeding mode of the nucleon.
Right, but the issue for us is it really needs 3 part, we need 2 meson, 1 baryon operators in there to really, we think, see it, so. That's an extension of what we've been doing, so that'll be fun. All right, thank you very much.
Thank you for the fantastic talk.
New addition. When you said, let's say, delta, 6 times mass of Y, right? Yeah, it's 280, I should multiply by 6, or, you know, what is it, what is it, I mean, numerically it would be for delta.
Are you talking about the G factor?
The mass, you saw the 6.2 and say it's looking too low if you plug in M pi equal 140.
Yeah.
But I think you were not working.
No, that one was at the D200, so I think that's at 200 MeV.
200.
Yeah,
I see.
and then typically, at larger pion mass, the nucleon and delta, they go up quite a bit.
But what about exotic stuff?
There was very nice.
Which exotic stuff?
The tetra quark.
It's just exotic, States.
Tetraquark? I actually took out the tetraquark for my time. We did a study of the cap, we tried to look at the kappa resonance. And we discovered something horrifying. We discovered, this was Danny Darvish's, one of my last students' theses. We put in like tons and tons of, the thing we wanted to ask is, do you really need a tetraquark operator in there? Or do meson-meson operators enough to see the kappa resonance? So there, we put in hundreds of different types of tetraquark operators, and we discovered that for a handful of them, it did produce an extra level. Right. Because the tetraquark is a tough thing to compute. But it showed that if you want to apply Lucier, you can see that if you miss a level, you're in trouble. That determinant, to get the right K matrix, you got to describe all of those crossings. You miss one, and if you don't have the tetraquark operator, when you're studying the kappa, you miss a level. And so and that's what people have done. So everything related to the kappa from anybody doing the last QCD who did not use a tetraquark operator, which means everybody, got it wrong.
What about the DD star, like these?
I have not worked on that. There are people that have looked at that, and again, you actually need these tetraquark operators. They don't look very different. Somehow they are.
It just, you jogged my memory, because when I was a grad student, I worked on kaons fermion interactions, and actually, there is a K-bar fermion bound state corresponding to lambda 1405. That was the good discovery I made in my thesis, but it's now forgotten. But it is positive for the SCAR model, of course. Like very approximate model.
Yeah, there's something very interesting going on in that region.
Yeah, I know there are many papers on lambda 1405
Yeah.
over many years.
Yeah, Ulf Meisner,
Yes.
every time I put out a paper and there's some new paper that he said we got reference. On the early 90s. I thought I got them all, I think, oh, you missed this one.
Yeah, maybe.
So I have a question about the string rating results that is mentioned. So, can you summarize what you see? So, for example, does the string rating, is it scale, go like the mass of the quark divided by the string? These colors.
Oh, how's it go with respect to the quark mass dependence?
Yeah, with the quark.
Yeah, that I,
The string rating, that scale, the work that you with the joke.
I do not recall. That's a paper that I wrote the code for, and I gave it to a grad student, Vanessa, and then I never heard from her for years. And then all of a sudden a paper appeared. What? So I was busy doing other stuff, so,
Do you think we discussed?
but you can read the paper yourself if there's some plot in there. I don't recall that fact. I don't remember seeing that fact. But I don't. What did I do?
It's one that I said. If they're not, another responsibility.
I think we looked at this three different masses. 2024, so you think I'd remember it, but. All right, thank, and we could, and I'll look too, and then you come and get me and we'll find.
BB and BB star, roughly?
BB bar and BS.
Oh, okay, look that.
Yeah.
Okay, well, let's thank Colin one more time.